So what we're going to do is use this recipe and show you how to do the rounding. So under step 1, it says write the answer in scientific notation. So if we would like to write a number in scientific notation, then we would need to write that as, scientific notation means that we have 1 digit followed by a point, followed by a comma, followed by the remaining digits, and then times 10 to some power. So we write 0.086, we write that as 8.6 times 10 to the minus. I would need to move this comma 1, 2, 3 spaces. So it's times 10 to the minus 3 meters. That's the first step of the recipe. The second step says divide the number by the power of 10. And that's another way of thinking of that is just to ignore this power for now. We're not going to look at this power. We're just going to look at the number in front, okay? And in step 3, it says compare this number in front to the number 3.162, which is the square root of 10. So every time we look at the number in front, we're going to be comparing it to this number 3.162. And we're going to use this comparison to tell us how we should do the rounding. If this number in front is bigger than 3.162, then we're going to round this number to a 10. If it's less than 3.162, we're going to round this number to a 1. That's what step 3 says. So in this case, we have 8.6 is bigger than 3.162. So we write this, we round it up, we round it to a 10. So this then becomes 10 times 10 to the minus 3 meters. 10 times 10 to the minus 3, if we multiply this 10 in, we can rewrite this as 1 times 10 to the minus 2 meters. And 1 times anything is, just itself. So it's 10 to the minus 2 meters. Then is the solution for the rounding rule of the first quantity. As you can see on the bottom left of the slide, just above my head, that's the solution of it rounded. Let's apply this recipe to the second example. Here we have the second example. Well, the first step I should do is I should write it in scientific notation. So writing this in scientific notation, this would be 2.1 times 10. Again, I need to move this decimal place 3 points. So again, it's 10.1 times 10 to the minus 3 meters. That's the first step. The second step says, we should ignore this power and we should just look at the number in front. So here the number is 2.1. We should compare 2.1 to 3.162. Here we see it's less than 3.162. So instead of making this a 10, I'm going to round it down to a 1. So here we have 1 times 10 to the minus 3 meters. Again, anything times 1 is just itself. So this is 10 to the minus 3 meters. So it means that that's using the rule, this number is approximately close to approximately 10 to the minus 3 using these rounding rules. The third example we have is 720 meters. If I write this in scientific notation, then it's going to be 7.2 times 10. This time it's going to be a positive power. So it's 7.2 times 10 to the 2 meters, right? The second step says we ignore this power. We don't look at the power. We just look at the number in front. Well, the number in front this time is 7.2. 7.2 is bigger than 3.162. So in this case, we're going to round this up to 10, and then we still have the 10 times 10 to the 2. And 10 times 10 to the 2 meters, that's the same as 10 to the power of 3 meters. So this is the solution then for this number rounded to an order of magnitude. If you think about it, it kind of makes sense, because what we've done is we've said 720. It's close to 1,000. So we've said into order of magnitude 720 is close to 1,000. It's certainly a lot closer to 1,000 than to 100. Now we move on to look at the solution to the problem we discussed before. How many table tennis balls can fit in a room? In these kinds of questions, it's good to know sort of the equations for calculating the volume of different shapes, possibly a sphere, a cube. In general, for different problems, it might be also good to remember the equation for density of an object as listed here. But back to our problem. We asked to calculate how many table tennis balls can fit in a room. So according to this, you'll need to make a number of assumptions, and you'll need to list those assumptions, and you'll also need to estimate different quantities. So the assumption that I've made is that the size of a room is 10 meters by 15 meters by 8 meters. So this is a really large room, a lecture hall. Of course, if you had assumed it's smaller, maybe a bedroom, that would have been fine, but just list your assumption and provide the dimensions that you've assumed it to be. Secondly, we need to estimate the size of a ping pong ball. So, a ping pong ball, it might be, I've estimated it in the order of 6 centimeters. Take a look on your ruler and see how big 6 centimeters is, see if you agree with that. It's just an estimate, right? Of course, the ball is a spherical shape, and the volume for a sphere is 4 over 3 pi r to the 3. If you think about ping pong balls, and if they're packed in a box in a room, then the shape that they actually take up is a cube. In that the ping pong balls, they will be sort of next to each other, and they will be touching each other from all sides, right? So the volume, the space that each occupies, including its little interball gaps, it'll be the shape of a cube. So for that reason, for this problem, you could just as well use the equation for a ball or for a cube. The method that we're going to use is we're going to calculate the volume of the room, and then we're going to divide that by the volume of one ball. So if I go ahead and do that calculation, the volume of the room is going to be the length times the breadth times the height. So this is going to be equal to 10 meters times 15 meters times 8 meters. The volume of one ball. So remember, it will be the length times the breadth times the height. I'm going to use this cube. Length times breadth times height. So we need to work in centimeters. 6 centimeters is 6 times 10 to the minus 2 meters. Here we convert everything to SI units. So it will be length times breadth, and then times 6 times 10 to the minus 2 meters again. I ran out of space there. And if we calculate what that is, then you can calculate it for yourself, but it's actually 5,555,000. It's actually this number of balls, 5,555,055 balls. So the next thing we need to do is, round this off to the correct order of magnitude. We spoke about that before. When we want to round something off to order of magnitude, the first step that we need to do is write it in scientific notation. So this is going to be 5.5, and you can count how many spaces you need to move the comma. 1, 2, 3, 4, 5, 6. We need to move it six spaces. So this is times 10 to the 6 balls, right? The next thing we need to do is we need to take a look at the number preceding the 10 multiply. So we look at this number here, this 5,5, and we compare this to the number 3.162, the number we compare it to. And we note that in this case 5.5 is bigger than 3.162, so that means that we're going to round this 5.5 to 10. So this is 10 times 10 to the 6 balls, which is of course 10 to the 7 balls. So there, we've done an order of magnitude calculation, and our solution is written as a power of 10, and we see the solution is 10 million ping pong balls. If you write 0.75 in scientific notation, then you can see we get 7.5 times 10 to the minus 3, which has two significant figures. 10.0, in this case the zeros are significant. The decimal point gives information about the reliability of the measurement. This final zero here, it's telling us that the measurement was 10.0 meters as opposed to 10.1 meters or 10.2 meters or something else. Whereas in this case, these leading zeros, they aren't significant. Our chapter, we're going to look at the rules for rounding. So the last digit retained is increased by 1 if the last digit to be dropped is greater than 5. The last digit remains as it is if the last digit dropped is less than 5. So this is simply the first 2 points are if the number to be dropped is greater than 5, we round off up, whereas if we less than 5, we leave it as it is. To illustrate this first rule, if the question reads round off to 2 decimal places, then the digit to be dropped in this case is this last digit. In this case, this last digit is less than 5, so we round this off, of course, to 13.45. It's covered by the first point. In this case, if we ask to round this off to 2 decimal places, here it's greater than 5, so this will be 13.46. We round off up. The last 2 points deal with what should we do if the last digit to be dropped is equal to 5. Well, the 2 cases. If the last digit to be dropped is equal to 5, the retaining digit should be rounded to the nearest even number. So here we can see the number to be dropped is equal to 5, and we need to round this 5 here off to to the nearest even number, which is 6. So this then will become 13.46. In this case here, we see once again we have the 5, but here we can see that already this is already an even number. So for this case, we don't increase the 6, we leave it as 13.46. Alright then, this concludes the first chapter on units and measures.